So this talk is about using laziness to make parallel programs run faster in Haskell. So we look mainly into the parallel coordination aspect that use laziness in order to achieve that improvement. So this is joint work with my supervisor Hans Floyd. So I will give a very quick overview of Glasgow parallel Haskell, the primitives and evaluation strategies before moving to the more advanced strategies and parallelism control mechanism, and then finally I will present some performance results of our experiment. So some motivation, what we want to achieve is higher performance through more flexible parallelism control. So how we do that is through the use of lazy evaluation and circular programming techniques. We develop a number of advanced parallelism control mechanisms and embed them into evaluation strategies and perform some performance testing on constructed test program and a few other applications to test how they do. So Haskell support semi-explicit parallelism for shared memory machine through the GPH extension. So GPH basically provides two primitives, one for specifying parallelism and the second for controlling parallelism coordination. So par is to specify parallelism in the expression x par y, which basically it returns y, and it's par x to be potentially evaluated in parallel. So a spark is basically a computation, a pointer to a computation which can be potentially evaluated in parallel, but it is up to the runtime system to decide whether it picks up that computation or not. Then we have PC to enforce sequential ordering, which is required in order to arrange parallel computation, given there is no default evaluation specified in Haskell. So it's basically the same syntax, XPCY, which returns the second argument, but in this case, X is evaluated to weak-head normal form. So basically, if we just use these two basic primitives, we can write a parallel program in Haskell in a very purely functional and stateless way. So building on top of these two primitives, we have the evaluation strategies library, which actually raise the level of abstraction even higher. So a strategy is basically just a function type. So a function of type A to eval A. So basically, it takes an expression and encapsulates it in a context, and that context basically encodes the parallel coordination of how to evaluate that expression. So if we run eval on that strategy, it basically return back the value and also kicking off any parallel coordination specified in the context. So we have corresponding strategy for the two basic primitives of GPH. So we have our par and our seek for the two basic primitives. So the good thing about using evaluation strategies is that it provides a very clear separation between coordination from computation aspect, and also strategies are compositional, and they are also higher order functions, as we will see in an example here. So this is basically a very basic sequential factorial implementation in Haskell, where the left and right can basically run in parallel. So the first step in parallelizing this using the primitives is basically we just say left or right, which basically annotate the left and says that left can execute in parallel of right, but we need the pseq as well there, which actually kickstart the parallelism. So this is how we do it using primitives. Now if we look at how we do it using evaluation strategies, we basically define the strategy separate from the algorithm. So basically this says the same thing as the previous one, but now in a strategy. So we use our par here, left, and our seek right. Then we just say apply the strategy with the using keyword. So we say using strategy. So basically this has the same behavior as the previous code. So this is side-by-side comparison. So in the right side, we see that there is a clear separation of coordination from computation code, and it also leads to more structured parallel program. So the evaluation strategies library contains some already defined strategies for data parallel, for example, data parallel on map mainly. So here we have a map in Haskell, for example, the map f, a function f on a list x. So how we specify data parallel on this map, we basically just put this in our code. So parlist is an example of a higher order strategy, which basically says that apply the function f to each element in parallel. So for each element, it creates a spark. And the second argument, which is also a strategy, but this argument actually specifies the evaluation degree. In this case, well, we can specify either weak head normal form or deep-seek, which basically evaluate to completely normal form. So we can do other things like chunking to control granularity. So for example, this, again, the sequential parts remain same, so it's only we just use a different strategy and we include an additional parameter size here. So basically, instead of creating a spark for each element, it creates a spark for a chunk of elements from the list. So now we move to tree strategies, which are actually more interesting strategies and also more challenging given the non-contiguous nature of this particular data type. So we have implemented two classes of strategies. We have the basic strategies, which are basically are more general. So they either use no parallelism control at all or some basic control mechanism. For example, we have part 3 and part 3 depth, which we will look in a moment. And then we also have a set of advanced strategies which use advanced mechanisms and are more flexible, and they use laziness inherently and some a technique which we call fuel-based control. So for example, of these advanced strategies, we have lazy size computation and the different variants of the fuel-based strategy, which we'll see in a bit. So here, this is an example of a tree. So the blue dot is a node, and so coming up with a basic naive strategy is very straightforward. So basically, we implement part 3, which is analogous to part list. So basically, this creates a spark for each element in the list. And so there's uncontrolled spark creation, and if the tree is quite large, especially if the size of the computation in each node is too small, this will basically lead to a high overhead. So this basic strategy is basically implemented through the traverse function if we make our tree data type an instance of the traversable type class. So now we start with doing some basic thresholding. So basic control. So first we have depth thresholding with part 3 depth. So on the top right corner there, we have some basic properties about the dynamic behavior of the strategy. So the information flow is about how administrative information to control the parallel coordination of the strategy flow in the tree. The context is about how much information is required to actually generate parallelism, and of course a parameter, in this case it's d. So d is a depth counter which is passed from the root down the tree. So this is the information flows down, and the context is basically the path length that we specify with d. So for example, in this case, if d is free, basically sparks are created for only the top d level on the tree. So this is very simple, low overhead and predictable parallelism. So it works pretty well for regular tree, but the problem, it lacks flexibility. So especially for unbalanced trees, and the parallelism may not actually reside in the top d level that we have sparked. So we have another basic parallelism control, which we call size annotation. So in this version, we basically use the size information on each node before creating a spark. So if the size is already encoded in the tree, that is fine, you can make use of that. Otherwise, we have to synthesize the size in a single annotation path. So that is why the information flow is up. So you see, for example, we have the size information here now, and we ensure that sparks are not created for smaller subtrees. For example, in this case, if S is less than 20, we don't create a spark for that. So as we could expect, because of the additional cost of doing an annotation, it carries some administrative overhead. Now we move to some more advanced mechanism which uses laziness inherently, and the first example is lazy size computation. So unlike the previous strategy where we saw that we need the global size information, in this variant it actually removes the need to do an initial annotation traversal, because at each node we basically lazily check if we have sufficient work at a particular node before sparking, creating a pointer to parallelism. So this function, which checks the size bound, basically returns true when it has established that the subtree contains at least the amount of element we are looking for, without doing a full deconstruction of the tree. So this lazy size check function is implemented using algebraic natural instead of an atomic integer. So the second advanced mechanism which we have is fuel-based control. So fuel is a limited resources which is distributed among nodes. So this is similar to potential in amortized cost, or the concept of engines to control computation in scheme. So using this mechanism, basically parallelism generation, that is sparks are created until the fuels run out. So it is more flexible to throttle parallelism. So the flexibility also offers the flexibility of defining custom function specifying how fuel is distributed among subnodes. For example, we have Q, look ahead, perfect fit, and split, and also give back, which we'll look in a moment. So the split function actually influences which path in the tree will benefit most of evaluation, parallel evaluation. So we'll look each distribution method one by one to see how it works. So first we have Q. So in the Q, the fuel flow is down, the context is local. So basically this is fairly simple. So fuel start from the top, we have an amount of fuel, and this is distributed equally among subnodes. Okay, but there is a problem with this one, is basically fuel is lost when we meet outer nodes. So this is a problem of this distribution. How? So in order to fix this one, we have a different variant, so which is called look ahead. So basically this version, what it does, it just look ahead and level down at each node to establish if there is enough computation before giving any fuel at all to that particular path in the tree. So this version is more efficient distribution. Then we also have a perfect split, as its name suggests. It distributes fuel perfectly among the subnodes based on the size, node sizes. So the context is global for this one because we need the size information for this one to work. Then a more interesting variant of the fuel strategy is give back version. So the give back version is has bidirectional fuel transfer. So the way it works is fuel is initially passed down from the root, and if fuel is given back if it is empty or is unused, and that fuel that is given back to the top node can be redistributed elsewhere in the tree where it is most needed. So this give back mechanism is implemented via circularity, and the fuel is represented using list of values instead of atomic integer. And this mechanism is basically more effective in enabling additional parallelism, especially for irregular tree, since a distribution carries deeper inside the tree. So if we look how fuel flow in this version, so the information flow is down and up in this case because fuel flows in two directions, context is local. And so initially fuel is passed down to subnodes, and then when we hit any outer node, the fuel is given back to the current nodes, and this is used redistributed elsewhere where it is needed most. So if we look at the code, how this is implemented in the code, so especially in the last 5 lines of code, so we see here initially fuels is split equally among the subnodes, and then each subnode gets the initial distribution of fuel here, and it returns any fuel that is not needed. So the fuel that is returned by the first subnode is injected to the second subnode, and the same for the second and the third subnode. And in the end, this fuel that is returned by the last node is passed again to the first. So this is how actually the circularity works, and the fuel flows back in a circular way. So here's a table of the strategies that we have looked. So we have first look at part 3, which is basically a simple strategy and has no parallelism control at all. And then we look at two basic strategy using basic parallelism control, the depth and the size annotation. But maybe the more exciting one was the lazy size strategy and the different variants of the fuel-based strategy, which actually exploits laziness for improved performance, as we will see in the results. So for the performance evaluation, so we initially use a desktop class machine, 8 cores, to test all the strategies, and we actually note very good performance across all the strategies. But the final target machine was a 48-core server class machine, so we could actually test the scalability of the strategies that we have defined. So this particular machine has 8 NUMA regions, so there is varying memory latency here because the remote region access is more than 2 times the local access, and it has 84 GB of RAM running Linux and running this version of GHC. So we use the parallel library, which includes the initial strategy library, and our data is the package that we're working on, which is an extended set of advanced strategies for tree-like data structures. It also includes heuristics for auto-tuning these strategies. So I'm not going to talk about heuristic in this talk, but all of the advanced strategies needs a parameter to work, and these can either be programmer specified, or we could either use these heuristic-based automatic parameter selection, which most of the time works better than a parameter that is specified by the programmer. And for applications, I'm going to present some results for a constructed test application and the bounce and hot algorithm, but there's more of that we have done. You can see it in the paper. So this is a constructed test program running on 84 cores, and there are 100,000 elements in the tree. So the tree layout has normal depth distribution, and the computation in each node is varying, so heterogeneous computation at each node. And the line in blue is the lines are the fuel-based strategy, and the dark one are the basic strategy, and the green one is a lazy size strategy. So we note a performance improvement of over 18% for the best fuel version compared to the depth-based strategy. So this is some interesting results. And so if we look at the some of the statistics of this run, so like the amount of sparks parallelism generated for depth, for example, it is fairly static. So this is it remains flat after a specific number of cores, whereas for the fuel-based strategies, it increases steadily with increasing amount of cores. And also the fuel give back actually generates more parallelism, given that the fact that fuel is redistributed elsewhere in the tree, so it ensures that we generate more parallelism. So this is some statistic about the give back hit rate. So for example, in this case, if we use fuel 100, so there are 478 instances of hit. So this is the amount of time that we have hit outer nodes, and the fuel is redistributed elsewhere in the tree. So maybe more interesting result is the balance and hot algorithm, which is more realistic and concrete application, and we use quite a large input of 2 million bodies and taking the measurement for one iteration only. And the body distribution in this case is multiple cluster distribution, and we perform the force computation in parallel. So one important thing to note in this is that there is no restructuring at all needed in the sequential code. So basically we just apply our strategy as we have defined, and we note improved performance. So the main thing to see here, the basic strategy, depth and size annotation perform worse than the fuel-based strategies. And this is also fuel-based, this one, but compared to the other fuel-based, it requires a global context, as we have seen earlier. And also the size annotation depends on a global context. So this may be the reason why the bad performance of these two and the depth strategy. So in this case, the pure fuel gives the best performance. This may be because it is simple, but it has cheaper fuel distribution. But still, the look ahead and give back is still within 6 to 20% of the best fuel. But we believe that we can make more improvement to get a better result from this strategy. So we also know that we have some overhead that we pay for the fuel strategy, around 15% for this input size. But still, I think it is a price worth paying for the flexibility we get as we get improved performance. So in summary, so we use laziness to improve parallel performance. We use laziness and circular programs in the coordination code to achieve additional flexibility. We developed a number of flexible parallelism control mechanisms in the form of evaluation strategies. We demonstrate improved performance on a constructed program and non-trivial applications as well. There's more in the paper. Especially application has very irregular tree. So this is a quick thing about the ongoing work. So we are now developing similar strategies for graphs, and we have mostly done with depth first and breadth first basic traversal strategies on graphs. So we're basically going to apply the same techniques that we have used for thresholding, fuel-based control, and also use laziness for graph strategies and implement some graph algorithms that use these strategies. So this is within the context of the 6-numbered core challenge, which you may look later. So the full paper, sources, and test programs are available online, and any comments and suggestions are welcome. Thank you.
In the interest of time, maybe one quick question.
So I was interested in whether you have systematically tried to assess the overhead that basically hurts you in the Barnes-Hut implementation as you already commented.
So
because it appears to be quite expensive to redistribute the fuel optimally, and that kills you really beyond the
so yeah, this is one thing that we have counted especially for this speaker input. So we do know that there is an overhead 14 plus 2, so around 15 for this particular algorithm. But we also think that we basically get good improvement up until around 32 cores. For a Barnes-Hut algorithm, this is pretty good, especially using Haskell and it's purely functional code. But we believe that it is also due to maybe the specifics of the algorithm, which is far more complex, and also of the runtime system, and maybe because of the machine, as I said previously, that it has 8 NUMA regions, and this is quite a large input. Maybe that is one of the reasons. But yeah, I mean, this is the only number that we have so far. And yeah, if we look at the garbage collection as well, we managed to do some optimization to kind of decrease the overhead of this.
So just generally speaking, people often say that when you become too smart and too sophisticated, typically you drown in the overhead.
Yeah.
What you have achieved.
Okay, let's thank the speaker again.